So remember, we've just seen that we can express y minus x beta hat norm squared as identity in n dimensions minus h for a specific matrix H epsilon norm squared. And then we said that we can write H as v1, v2 times identity p, 0 and minus p, v1 transpose, v2 transpose, where the columns of v1 are orthogonal, and so are the columns of v2. So in other words, this whole matrix is an orthogonal matrix. So that means, in turn, that I can write in minus h as, because it's orthogonal, so this is in minus v lambda, so this was lambda, v transpose. Now this is the same as v transpose minus v lambda v transpose, because v is orthogonal, so these two are inverses of each other, which is v identity in n dimensions minus lambda v transpose. In other words, plugging in this expression there, this is v1 v2 times, so if I take the identity minus this, then this is going to be a 0 matrix in p dimension and identity matrix in n minus p dimensions, v1 transpose v2 transpose. Or if I want to go one step further, we see that the 0 part doesn't really matter. This is going to be equal to v2 transpose. OK, so what does that mean for the distribution of this quantity? Well, it's just going to be the Euclidean norm squared of some multivariate Gaussian variable, namely this matrix times epsilon, right? And we just said that we can write this as v2 transpose. So in other words, y minus x beta hat norm squared is the same as v2 transpose epsilon norm squared. Now remember, v2 is an n by n minus p matrix. And its columns are orthogonal, so that means this matrix is norm-preserving. So the norm is the same as the norm of v2 transpose times epsilon. So, and this is, again, a multivariate Gaussian random variable. So let's try to understand this variable to understand what actually its distribution is like. So the mean of this variable will be 0, because epsilon has mean 0. Let's write it down. And now, more importantly, what's the covariance? The covariance matrix of v2 transpose epsilon is the expectation, because everything's mean 0, of v2 transpose epsilon, epsilon transpose v2 transpose. That's just v2. Now v2 can be pulled out. We have the covariance of epsilon in the middle. Covariance of epsilon is sigma squared times the identity. So this is v2 transpose v2. And this part here, because they are orthogonal, or composed of orthogonal columns, it's sigma squared times the identity in n minus p dimensions. Perfect. So now you have it. The quantity we're computing here is nothing but the norm squared of a multivariate Gaussian random variable with identity covariance matrix, except for scaling sigma squared. That means that if I take 1 over n minus p and also divide by sigma squared, then this quantity follows a chi-square distribution with n minus p degrees of freedom. And all the work we did was just to see what is the correct scaling of this and what is the correct number of degrees of freedom. So you can probably already tell what we're going to do. We are trying to get back to our original hypothesis testing problem right here. And we want to divide by something that follows that's the square root of the corresponding chi-square distribution here. What remains to be seen is that actually this quantity here is independent of beta hat that we want to plug in here. So before we do that, just one more thing. So we were always considering the maximum likelihood estimator, and we could still do that. By what we just wrote down, we know that if I renormalize the maximum likelihood estimator, so if I multiply by n to get rid of that n and divide by n minus p, and also divide by sigma squared, then this follows the chi-squared distribution. So in other words, let me just define a new estimator here, sigma squared unbiased, as the same thing where I divide by n minus p instead. One thing for you to do once I erase this board is, why don't you check what the expectation of the actual MLE is? It is not going to be unbiased, but given what we just did, it should be straightforward to see how much the bias is of this MLE. OK, so let's quickly continue here. So the only thing that's missing is trying to figure out if this is indeed independent of the thing that I want to divide it, that I want to put in the numerator. And how do we do this? We will express U transpose beta hat also in terms of our matrix H. So what is U transpose beta hat? This was U transpose X transpose X inverse X transpose Y. Let's plug in the ground truth and the noise. We've already seen that this is U transpose beta star. This goes away, plus the noise term, which is X transpose X inverse X transpose epsilon. So this is a little bit annoying. We would be really happy if there was an X in front of this here, because then this would be exactly H of epsilon. It's not the case, but it's not that bad either, because we are only thinking about dependence here. And if I take a map of individual components that are independent, then they will remain independent. So the insight that we need here is that this can be written as the following. Bear with me. Oh, not an equal sign, a plus sign. Bear with me. We can write exactly the same thing, but squeeze in an additional H matrix. So we want to squeeze in X, X transpose X inverse X transpose epsilon. Why is that true? Because X transpose X cancels out with one of those inverses, this one, for example. And what we end up with is X transpose X inverse X transpose epsilon, which is the same as here. So in other words, we can express the error in our estimator as H epsilon. And now this is, again, an unbiased Gaussian random variable. It's a linear transformation of the original epsilon. And H epsilon and, where do I have it, V2 transpose epsilon are jointly Gaussian, because they both come from the jointly Gaussian random variable epsilon. So all that remains to show independence of these two random variables is to compute their covariance. Why don't we do that? Let me amend this by saying that H can be expressed as V1 transpose. And then we have that covariance of H epsilon and V2 transpose epsilon is the expectation of H epsilon transpose V2, which is the expectation of V1 transpose epsilon transpose V2. This thing here has covariance matrix sigma squared times identity. So this one, expectation of epsilon transpose is sigma squared times identity. So here we have V1 transpose hitting V2 transpose, but that is nothing but the inner product of column vectors in V1 with column vectors in V2, and the original matrix was assumed to be orthogonal. So that means these vanish. So this is the 0 matrix, and applying the V1 matrix again doesn't change that. So in fact, we have 0 covariance, and because they are jointly Gaussian, we can conclude that first, H epsilon is independent of V2 transpose epsilon. And because we can express our estimator for sigma hat squared by this quantity and our estimator for beta hat by this random quantity, in turn, we get that sigma hat squared unbiased is independent of beta hat. And this is going to be enough for us to finally write down the pivot and the test statistic once I'm done erasing.